What if the universe grew up faster than it was supposed to? For decades, cosmologists built simulations of how big matter clumped together after the Big Bang, how the first stars ignited, and how galaxies slowly assembled over billions of years. But in 2025 and early 2026, the James Webb Space Telescope started sending back data that doesn't quite follow that script. Galaxies that look too mature, black holes that may be growing too fast, invisible dark matter mapped in unprecedented detail, dust forming where it shouldn't exist yet. Individually, each discovery is fascinating. Together, they raise a bigger question. Did we underestimate how quickly the universe learned to build itself? Let's start near the beginning. Webb pushed the observable universe closer to the Big Bang than ever before by confirming a galaxy called MOM Z14. We're seeing it just 280 million years after the Big Bang, when the universe was about 2% of its current age. If the universe were a person, this wouldn't be a teenager. It would be a cosmic toddler. And that matters, because structured galaxies are not supposed to exist this early without long periods of evolution. Yet Webb isn't just detecting a faint blur. It's confirmed this through precise infrared measurements and redshift analysis. As the universe expands, light stretches into infrared wavelengths. Webb measures that stretch, the redshift, to determine exactly how far back in time we're looking. And every confirmed galaxy this early forces us to test whether our models of how quickly matter clumped together are actually correct. We're not just finding something far away. We're watching the universe build itself. But MOM Z14 wasn't the only surprise. Webb also found a galaxy called Alaknanda, a near twin of the Milky Way, forming just 1.5 billion years after the Big Bang. That's extremely early for something this organized. Most galaxies at that age are chaotic, clumpy, still assembling. But Alaknanda already shows a rotating disk and recognizable spiral structure, and it's forming stars at about 60 suns per year, far more active than our galaxy today. That tells us gas cooled and settled efficiently. Its gravitational dynamics stabilized early. So, what does that mean? Either galaxies organize themselves faster than our simulations predict, or something was helping structure form more efficiently. That something could be gravity behaving in ways our models don't fully capture, or it could be dark matter, the invisible scaffolding that normal matter falls into. If Alaknanda formed this cleanly, this early, those dark matter halos may have collapsed and stabilized sooner than expected. Every too mature galaxy Webb finds adds pressure on our assumptions. And that leads directly to the next discovery. Because Webb didn't just observe galaxies, it mapped the invisible structure beneath them. In January 2026, NASA released one of Webb's most important achievements, one of the most detailed maps ever made of dark matter's influence. Dark matter is invisible. So how did we map it? We watched what it does to the light around it. Massive clumps of dark matter bend background light through gravitational lensing. Webb measured tiny distortions across hundreds of thousands of galaxies and reconstructed where dark matter must be located due to the gravitational lensing around the galaxies. The result? A vast cosmic web, dense nodes connected by filaments, with visible galaxies tracing that hidden structure. Dark matter appears to be the universe's structural backbone. But here's the key. Webb's precision is now high enough to test whether our dark matter simulations are actually correct. If the map shows subtle mismatches, we may need to refine how we understand dark matter's behavior. This isn't just a prettier map. It's a stress test of the universe's foundation. And if structure formed early, we also need to ask what else formed early, including something much smaller but equally important: dust. Webb also observed Sextans A, a chemically primitive dwarf galaxy, an analog for early universe conditions. Scientists expected it to be nearly dust-free. Instead, Webb found complex dust, including metallic iron dust and silicon carbide. That's surprising. Dust usually requires heavier elements formed in stars. In metal-poor environments, there shouldn't be much of it. Yet, it's there. Remember, in astronomy, metals are any elements heavier than hydrogen or helium, the raw materials for rocky planets. Even more surprising, stars in Sextans A appear to be forming iron-rich dust grains in ways never observed before in early universe analogs. Dust plays a critical role in galaxy evolution. It cools gas, helps form stars, seeds planets. If dust forms more easily than we thought, the early universe may have been chemically complex much sooner. And then Webb found something even stranger. Not galaxies, not dust, but compact objects that may be powered by rapidly growing black holes. In January 2026, a major paper described a population of mysterious objects called little red dots. These are compact, luminous sources with unusual spectra, blue in the ultraviolet, red in the optical, with broad emission lines that don't fit normal galaxy templates. They are blue in the UV because of intense starburst or accretion, but shrouded in so much dust that the light stretches deep into the red by the time it reaches Webb. Over 100 have now been studied. Many show features similar to active galactic nuclei, bright regions around feeding supermassive black holes. In some cases, the black holes appear to outshine the entire host galaxy. If these are rapidly feeding black holes in the early universe, that could help explain how supermassive black holes grew so quickly. Standard models struggle to grow billion solar mass black holes this fast. Webb may be revealing the growth engines themselves. So, let's take a step back. A galaxy from when the universe was a cosmic toddler, a spiral galaxy that looks too mature, a detailed map of invisible dark matter scaffolding, dust forming earlier than expected, and black holes possibly growing faster than our models allow. Individually, these are discoveries. Together, they're pressure. Pressure on simulations, pressure on assumptions, pressure on how we think about the universe and how it grew up. Webb isn't just giving us prettier images, it's stress testing cosmology as we know it. So I want to know what you think. Are these refinements, or are we approaching a shift in how we understand cosmic evolution? Let me know in the comments, and if you enjoy breaking down real astrophysics without the fluff, subscribe, because Webb clearly isn't done surprising us. See you in the next one.